Class, we're going to now have a 4.26 to 4.28 review the three type of quadratic trinomials. Okay, and just a quick reminder: a quadratic trinomial is when the highest power is 2, in which there are 3 terms trinomial. So let's get into example 1. Convert the quadratic trinomial to vertex form. Identify the vertex point and the roots of the function. Then sketch the graph. Let's begin. And because we need to identify the roots, which means it's the x-intercept when we have an x value when y is 0, we're going to need to substitute that y value in for 0. That is the first step of which we do. After we do that, we need to change this term, the constant, and move it to the other side of the equation. And we do that by adding 9 to both sides of the equation. Now we have 9 equals x squared plus 8x. This now allows us to have just the a and b terms equaling to a constant, which gives us space to add a third term, which is going to be b over 2 squared. We have to add this term to both sides of the equation to maintain its balance within that equality, right? Therefore, we need a state of b value, which is 8. We can just move this to the side. So if b equals 8 and we're using this formula, b over 2 squared, we're then going to have 8 over 2 squared, which is 4 squared, which is 16. Therefore, we must add 16 to both sides of the equation. 16 plus 9 equals x squared plus 8x plus 16. So now we're going to add these two values together. That gets us 25. And we're going to factor this perfect square trinomial. And we know it's a perfect square trinomial because using this equation, we then find that we have 2 of the same binomials that when we either use FOIL, the box method, we're going to get this quadratic trinomial. So it's a perfect trinomial, perfect square trinomial, because the two binomials are the same values, have the same values. This can be written as now 25 equals the quantity of x plus 4. Again, they're both the same, so we can just make it as x plus 4 squared. Side note, because we were asked to find that vertex form, we're going to move this to the side real quick. And if we were to subtract that constant back into the other part of the equation, yes, it does equal 0, but because we only have one variable on one side of the equation, putting it all together, we actually now have the vertex form. In which, when this value is positive, when we have a plus 4, the x value in the vertex point is going to be negative. And because this is a minus 25, the y value is also going to be negative. So our vertex point is negative 4, comma, negative 25. This is our vertex points. And by looking at the vertex form in the equation, because the a value is positive, we know this is going to be a minimum vertex point. into solving for this equation and identifying the two roots. We need to get rid of that squared. So if I was to square root it, which is the inverse operation of squaring, I then cancel that squared, and now I have the square root of 25 equals x plus 4. Okay, so this is what we're going to now called separate and solve. We're going to separate into two separate equations in which we have that square root of 25 equals x plus 4, square root of 25 equals x plus 4. But knowing the square root property, the square root of 25 is when it is positive 5 and when it is negative 5. So that x plus 4 equals both positive 5 and negative 5. Now we can solve for the x value by subtracting 4 to both sides. 5 minus 4 is 1. Therefore, x equals 1. Our x-intercept is 1, comma, 0. And when we subtract 4 to both sides, we have x equals negative 9. Our point is negative 9, comma, 0. You should write the final answers just like here. These are our roots. So let's begin. Our vertex point is negative 4, negative 25. So 1, 2, 3, 4, negative 25 all the way down here. Our roots 1, 0 and negative 9, 0. And 1, 0. Now we are just going to connect the points. So now for example 2, when y equals x squared plus 8x minus 4, we're going to continue on and going through this process of solving for the roots and the vertex points and such. So just like before, 0 is equal to y, so we make that substitution. We are going to change 4 and put on the other side of the equation, so that constant term is now equaling to the rest of the equation. We're going to identify our b value, which equals 8. Therefore, when we divide it by 2 and square it, we are left with 16, in which we're adding to both sides of the equation. So now we're left with 20 equals x squared plus 8x plus 16. We're then going to factor out the quadratic trinomial because they're the same quantities. It's now x plus 4 squared, and when we square root, then to identify in the vertex form, right, 20 equals x plus 4 squared. If we were to subtract 20 to both sides, 0 equals x plus 4 squared minus 20. However, it's now in the vertex form. And here is our vertex form, in which the vertex point is going to be a minimum, because a equals 1, and a positive 1, in which the point is negative 4, comma, negative 20 as our vertex point. So now moving on back to here, we need to get rid of that square. So we square root. Now we're left with square root of 20 equals x plus 4 And now here are when things are going to get different. We're still going to separate and solve, right? So we have now square root of 20 equals x plus 4, and square root of 20 equals x plus 4. So on this side right here, we need to simplify this value because it's not a perfect square, right? 20 is a composite value that has a factor of a perfect square, which is 4 and square root of 5. And just like we learned before, when we're doing this, we always want a perfect square being multiplied by a prime number. So then when we simplify, we have now 2 square root of 5, and we just substitute that value in for square root of 20. But let's not forget that we're going to have a positive 2 square root of 5 and a negative 2 square root of 5. Okay? Because that square root property that we learned earlier, and anytime that we're square rooting, we're going to have a positive value as well as a negative value. And now let's subtract 4 to both sides. X equals negative 4 plus 2 root 5, in which now our point is negative 2 plus 2 square root 5, comma 0 as one of our roots. And then when we subtract 4 to both sides on the second equation, we're now left with negative 4 minus 2 root 5 equals x, in which our final point is negative 4 minus 2 root 5, comma 0. Here is our second point. Now we have enough information to graph. Our vertex point is a minimum at negative 4, comma negative 20. It's right here. We have our 2 points, our 2 roots, which one I'm just rounding to 0.50, comma 0, which is right here. And negative 8.50, comma 0, which is right here. So I can just make a nice rough sketch. 3, y equals x squared plus 8x plus 17. 0 equals x squared plus 8x plus 17. Subtract 17 of both sides. Negative 17 equals x squared plus 8x. Take that b value, positive 8 over 2 squared, 4 squared, 16, add 16 to both sides. Negative 1 equals x squared plus 8x plus 16. Now we can factor this perfect square trinomial. It is the same, 2 of the same binomials, so it's x plus 4, in parentheses squared. And then here is when things get interesting, because when we square root, as we normally do, right, to get rid of that squared, we're now left with a square root of a negative value. Okay, so let's see how this plays out. We're still going to separate and solve. Okay, so we have square root of negative 1 equals x plus 4, and square root of negative 1 equals x plus 4. So going back to here, the square root of negative 1 is 1i, or it's just I. So we just write it like that. X plus 4, subtract 4 to both sides. We have now negative 4 plus I equals x. our point is technically x plus I comma 0, but again, it's non-real. So it's not even graph. We can't even graph. Can't graph. Okay, and down here, now one would think that would be negative I equals x plus 4, subtract 4 to both sides, right? Negative 4 minus I equals x. And that's what you'll have. So negative 4 minus I comma 0. But again, it's not real. Can't graph. Okay? Now let's bring everything together. We have 3 different examples of which we have 3 different examples in which we completed the square in, and here are our results, right? The key thing to notice is that this what happens when we have a rational result, because we have a perfect square as our term. Here we have an irrational result, or irrational x-intercepts, because our final term is actually not a perfect square. Here, number 3, we have an imaginary result, because our C term, that I, is neither a rational or irrational number. It's just positive 1. We have an imaginary result because it is neither irrational or irrational result. The next major piece for you to understand is this concept of factoring. Okay? Before we even go into completing the squares, look at each of these problems and you have to ask yourselves, which of these am I able to factor? So for this one, what factors 17 gets us 8? Well, 17, the only factor 17 is 17 and 1, and that cannot add up to 8, so this is not factorable. So we need to complete the square. This is a perfect example of when we need to complete the square. Let's do x squared plus 8x minus 4. Well, factors of negative 4. 4 and 2, 4 and 1, 1 and 4, 2 and 2, switch them up between positive and negative. None of them will equal positive 8, so this too is not factorable. So you must complete the square. Okay, now let's go into x squared plus 8x minus 9. Well, actually, it is factorable, because what happens when I do the quantity of x plus 9 times the quantity of x minus 1?